Hey everyone, thanks for joining the live stream on BioniChaos. Today, we're diving into another exciting session where we'll explore biomedical data processing tools and how they're developed for interactive web applications. If you're new here, welcome. This channel is all about showcasing tools for working with data like EEG and ECG signals, all designed with a fun, engaging approach. We avoid using cloud services like AWS or Google Cloud, and everything's done right here on a single page to give you a seamless, interactive experience. Feel free to ask questions in the chat, give feedback on the projects we're showcasing, and if you want to support the channel, you got it. No mention of the money side. Let's focus on the tools and development projects. For those tuning in, we've got a bunch of really cool tools in development. Right now, we're working on interactive biomedical data processing applications. These tools are built specifically for signals like EEG and ECG, and they're designed to run directly in your browser. Everything we build is centered around a single screen experience, meaning no pop-ups, no distractions, just seamless interaction with the data. Some of the tools we're working on include Seizure Zone. This is an ongoing project where we're aiming to visualize and analyze EEG data, helping us better understand seizure patterns. Other biomedical signal tools, we're experimenting with different kinds of data, so there's always something new on the horizon, be it vision, hearing enhancement, or data processing from common hardware like cameras and microphones. Each tool is designed to be accessible to everyone, whether you're a data scientist or just curious about biomedical data. We focus heavily on client-side processing, so you can dive right into the data without needing a server-side infrastructure. Feel free to ask about any specific projects you're interested in, or drop suggestions in the chat. This Python script is designed to help you maintain and monitor the structure and health of your website by generating a sitemap and logging potential issues. It starts by specifying a list of directories that should be ignored during the scan. The script then sets up 3 different log files, one for errors, one for links missing from the sitemap, and one for links found on the landing page. The core of the script revolves around the fetch page details function, which is responsible for retrieving each page's content and checking for problems. It looks for common error messages, checks whether the page contains important elements like a title and meta description, and ensures the page has enough content to be considered valid. To generate the sitemap, the Create Sitemap function scans the directories of your website, collects details for each page, and compiles an XML sitemap with URLs, last modification dates, descriptions, and titles. Looking at the XML output, it's clear that the script has successfully generated a sitemap with detailed information about each URL, including the page descriptions, titles, and any errors encountered during the crawl. Several of your pages return status errors, like 403, forbidden, and 500, internal server error. These errors likely indicate issues with either file permissions or server-side problems on those specific pages. For example, the pages like Seizure Zone and Nifty View returned a 403 error, meaning access to these pages might be restricted, possibly due to file permissions or server configurations. In some cases, the script flagged pages as missing essential elements, like the recalls page. This means that important parts of the HTML, like the page title or meta description, were not found, which could affect both SEO and user experience. On the brighter side, many of your interactive tools, like the 100-year EEG, CardioQuest, and RhythmScan, are functioning well and contain rich descriptions and titles. These pages seem well structured, allowing users to engage deeply with the content. Other issues involve pages with content flagged as too short, such as seizure fuzz, which suggests that either the page content is sparse or there may have been a problem during the content retrieval. In summary, while most of the sitemap is well populated, you'll need to investigate and fix the pages showing errors or missing elements to improve the overall website health. Let me know if you'd like help troubleshooting specific issues. It looks like you're showcasing the Cardio Rock tool, a game designed to challenge users in recognizing ECG patterns by providing a dynamic real-time rock curve. The interface is quite intuitive, allowing users to adjust the noise level of the ECG signal and see how that impacts the accuracy of their judgments on the rock curve below. The score is displayed at the top, along with an AUC, area under the curve metric, although the current screen says there's not enough data to calculate performance yet. The Rock C curve is a great visual feedback tool that helps users immediately see how well they're distinguishing between normal and abnormal ECG waveforms. The slider for adjusting noise levels adds an interactive element, letting users explore how the signal quality affects their diagnostic ability. Additionally, the option to change the interpolation method for smoothing the rocks curve provides more control over how the curve is presented. The overview at the bottom explains the concept behind the game, emphasizing how users can learn by actively shaping the ROS curve through their performance, instead of just crunching numbers. This is a clever and engaging approach to teaching important concepts used in medical diagnostics, particularly in fields like ECG and EEG analysis. This tool seems to be functioning well and offers a highly interactive learning experience for your users interested in biomedical signal processing. Let me know if there's anything specific you want to adjust or improve here. You're right to question the AUC, area under the curve value. It does seem off. AUC values typically range between zero point 0.0 and 1.0, representing how well a model or user distinguishes between positive and negative cases. Looking at the ROC C curve on the graph, it appears that you have some movement along both the true positive rate and false positive rate axes, which should yield an AUC higher than 0.1 Welliver. A curve that hugs the diagonal line would result in an AUC closer to zero point 0.5, representing random guessing, while curves closer to the top left corner, high true positive rate and low false positive rate, would indicate better performance, with AUC approaching 1.0. The low AUC value of 0.10 seems suspiciously incorrect given the visible plot. This could be a calculation issue in the backend where the AUC is being computed. It might be worth checking. One, data points feeding into the AUC calculation. Ensure that the true positive and false positive rates are correctly recorded and passed to the function that computes the AUC. 2. Calculation method. If you're using an existing library, ensure the correct method, like trapezoidal rule, is being used to compute the area. If it's a custom implementation, review the summing process over the points in the ROC curve. I would suggest running a few more tests and inspecting the data used for calculating the AUC, as the visual representation doesn't align with the displayed value. This app.py file is a straightforward Flask application that sets up a basic server. It initializes the application using Flask's core setup and defines a single route that serves the index.html template when a user accesses the root URL. The structure is minimal, indicating that the backend isn't doing much heavy lifting. Instead, it's primarily responsible for rendering the front end, where the actual logic of the CardioRock tool is likely handled by JavaScript. Running the app in debug mode is useful during development because it enables live reloading and detailed error reporting, making it. This waveforms.js file is generating ECG-like waveforms using a combination of mathematical functions for the P, QRS, S, and T waves of an ECG signal. Here's an overview of what the code is doing. It starts by creating a range of time values, t values, over which the waveform will be generated, corresponding to a time axis in terms of radians, scaled to cover 5 pi. The Gaussian function is used to generate the characteristic R wave, the sharp peak in an ECG, and this is wrapped into the refined R wave function to produce various QRS complexes. The code defines the full waveform generation in generate full waveform, which combines different sections for the P wave, QRS complex, S wave, and T wave. These components are added together to form the complete waveform, which mimics a normal ECG signal. Several variations are created for abnormal waveforms, such as missing P, S, or T waves, or modifying the QRS complex. These variations, QRS variation 1, no P wave, etc., simulate different abnormal heart rhythms. The array waveform stores a set of precomputed waveforms, normal and various abnormal ones. The function generate waveform is responsible for selecting a random waveform, either normal or abnormal. It uses randomness to determine if the generated waveform will be abnormal with a 60% chance, and selects from one of the defined variations. The overall goal is to simulate different ECG waveforms, some of which are normal and others abnormal. This is likely part of an interactive game or diagnostic tool, where the player or user is expected to analyze these waveforms and identify abnormalities. The code is well structured for creating realistic-looking ECG signals, offering variety in both normal and abnormal heart rhythms. It provides flexibility through modular functions for each variation, making it easy to expand with more complex waveforms or noise models if needed. If this is part of a broader application like CardioRock, it fits well with the idea of dynamically adjusting ECG signals for a challenge. This main.js file orchestrates the interaction between the user and the dynamic ECG waveform display, as well as the rock curve generation. The script manages several key aspects of the CardioRock tool, including rendering waveforms, applying noise, capturing user interactions, and calculating performance metrics like true positive and false positive rates. Here's a breakdown of what happens in this file. When the document is loaded, the script sets up two HTML canvases, one for displaying the game waveform and another for the ROC curve. It initializes various interactive elements, such as the noise slider and interpolation method dropdown, which allow users to modify the noise level in the waveform and change how the ROC curve is drawn, linear, spline, or polynomial interpolation. The game involves rendering an ECG-like waveform on the canvas, which moves across the screen from right to left. Noise is applied to the waveform using the apply noise to waveform function, and the user can adjust the noise level through the slider. The handle click function listens for clicks on the canvas and checks if the user clicked on an abnormal part of the waveform, represented by waveform type. Based on the user's performance, hits, misses, false alarms, and correct rejections, the score is updated and a rock curve is plotted. The rock curve provides a visual representation of the user's diagnostic accuracy, showing the relationship between true positives and false positives. Different interpolation methods, linear, spline, and polynomial, allow the rock curve to be drawn in various ways, controlled through the interpolate y function and its related methods, linear interpolation, cubic spline interpolation, and polynomial least squares fit. As the game progresses, new waveforms are generated and the noise level is applied to them. The game loop function handles the continuous rendering and animation of the waveforms and checks if the user has correctly identified abnormalities. Overall, this file combines interactive graphics, waveform display, and rock curve with user input, tracking the user's diagnostic performance. The rock curve and AUC calculation offer immediate feedback on how well the user is identifying abnormalities in the waveforms, reinforcing the educational aspect of the tool. If you'd like, we can now dive deeper into specific parts of the script, like improving the rock calculation or refining the noise application. In the code you shared, the area under the curve, AUC, is calculated using a custom method that approximates the area by summing up trapezoidal sections between adjacent points on the Rossi curve. Here's a step-by-step explanation of how the AUC is being calculated. 1. Storing ROC points. The rock points array stores the points that make up the Rossi curve. Each point consists of true positive rate, TPR, the fraction of actual positives correctly identified; false positive rate, FPR, the fraction of actual negatives that were incorrectly classified as positives, correct, a Boolean value indicating whether the user's guess was correct. 2. Sorting the rock points. Before calculating the AUC, the rock points are sorted by their FPR values. This ensures that the points are processed in order from left to right along the FPR axis. 3. Trapezoidal rule for AE. The AUC is approximated using the trapezoidal rule. For each pair of adjacent points on the rock curve, each representing an interval of false positive rates, a trapezoid is formed, and its area is computed. The total area of these trapezoids is summed to estimate the AUC. For each pair of points, x1, y1, and x2, y2, representing two consecutive Rossi points, x1 and x2 represent the FPR values. So y1 and y2 represent the TPR values. The area of the trapezoid between these 2 points is calculated by text trapezoid area frac y1 text midline y x1 plus y2 midline x2 2 times x2 to x1. The trapezoid is computed relative to the diagonal sum midline that runs from 0, 0 to 1, 1, as this represents a random guess scenario, baseline performance. The midline y function is simply y equals x, meaning the diagonal. 4. Summing trapezoid areas. The sum of the areas of all these trapezoids between each pair of rock points gives the total area under the curve. 5. AUC calculation. The final AUC is the accumulated sum of the trapezoidal areas. Issues with the current AUC calculation. Edge cases. The code currently skips calculations if there are fewer than 5 rock points, which may result in not enough data to calculate the AUC. Interpolation issues. If there are invalid or NaN values in the interpolated points, for example, if no points fall in a certain range, the code skips that trapezoid, which could lead to incomplete or inaccurate AUC results. Accuracy. The trapezoidal rule is a common method for approximating AUC, but it might not be accurate enough if the rock curve has sharp turns or is very irregular. Suggested improvements. To improve the accuracy of the AUC calculation, consider refining the interpolation methods or using a library function, such as from scikit-learn, that computes AUC with robust numerical methods. Ensure that all edge cases, like very few Rossi points or unusual distributions, are handled more gracefully, perhaps by providing default behaviors or warnings in such cases. Overall, the AUC is being calculated correctly using an approximation via the trapezoidal rule, but it may benefit from more robust error handling and possibly better interpolation for improved accuracy. The primary difference between your current code and the suggestions I provided lies in the systematic troubleshooting and interpolation methods, linear, spline, and polynomial, that might need better integration and more precise implementations. Let's break down the differences and explain the changes I recommended, focusing on making the interpolation methods and rock curve adjustments more robust. Key differences and suggestions. 1. Interpolation methods. In your current code, you have placeholders for cubic spline interpolation and polynomial least squares fit. While linear interpolation seems functional, the other two methods need proper implementations. My suggestion: I emphasized implementing or integrating reliable cubic spline and polynomial interpolation methods. You can either build a custom solution or use existing libraries. The goal is to ensure these methods accurately interpolate the ROC curve. For instance, for cubic splines, if you don't want to write the entire spline algorithm, you could use a library like cubicspline.js, like gith.github.com//spline. Alternatively, for polynomial fitting, libraries like numeric.js x github.com/l/numeric provide built-in utilities for matrix solving and polynomial regression. 2. Debugging and console logs. Current code. Your current code doesn't log values for each step of the interpolation, so it's hard to know if the interpolation method is working correctly. My suggestion: I recommended adding console.log statements to monitor the interpolation process. For example, logging values at key points, such as the coordinates and interpolated points, can help you trace whether the interpolation methods are computing correctly. Example for debugging: JS function linear interpolation x const points equals rockpoints.sort a b 8 fpr-b.fpr console.log linear interpolation points log points let y-x default to the diagonal if no points for let I points.length I plus const x1 points I minus 1 fpr const y1 points I mont tpr const x2 points I fpr const y2 is points I tpr console.log x1 y11 x2 y1 log points being interpolated if x equals x1 and x equals x2, y equals y1 plus x minus x1, y2 minus y1, swarf x2 minus x1. Linear interpolation break, return y. 3. Handling NaN values. Current code. You have some checks for invalid NaN interpolation values, but they may not comprehensively handle all edge cases where data points are sparse or incorrect. My suggestion: continue using warnings for invalid data points, but it's essential to ensure that each interpolation method gracefully handles edge cases like insufficient rock points or missing values. 4. Visual feedback for interpolation. Your code does draw the rock curve, but doesn't differentiate between the rock points and the interpolated curve, making it harder to see if the interpolation is working correctly. My suggestion: I recommended highlighting the actual rock points, TPR, FPR, separately from the interpolated curve. This would allow you to visually check that the interpolation methods are smoothly connecting the points. Example for drawing rock points: JS rock points.for each point will const x equals point.fpr toss rock canvas.width, const y equals 1 point.tpr rock canvas.height, rock ct.begin path, rock ctx.arcsy402 math pi. Small circle for each point, rock ctx.fillstyle ffro, red color for rock points, rock ctx.fill. 5. Testing the AUC calculation. Current code. Your AUC calculation is based on the trapezoidal rule. It's important to ensure that the interpolation method is producing accurate values before calculating AUC. My suggestion: use the updated interpolation functions to confirm that the rock points are being interpolated correctly. If the interpolation produces reasonable results, the AUC calculation will reflect that accuracy. Otherwise, errors in interpolation will lead to incorrect AUC values. 6. Cubic spline and polynomial interpolation placeholders. Current code. The cubic spline interpolation and polynomial least squares fit methods are placeholders. They need to be fully implemented to ensure smooth and accurate interpolation between rock points. My suggestion: fully implement these methods. If manual implementation is too complex, consider importing an external library to handle spline and polynomial fitting. For example, using the numeric.js library for polynomial fits or a dedicated cubic spline library will save development time and ensure accuracy. 7. Clamping values in polynomial fit. Current code. You already have clamping in your polynomial interpolation, math max 0, math min 1, y, to ensure that the interpolated values stay within valid bounds, 0 to 1. This is a good practice to prevent out-of-bounds issues. My suggestion, keep this behavior to ensure your rock curve stays within the defined space. Next steps to implement the changes. 1. Highlight rock points. Use the for each loop to plot rock points on the curve separately, giving you visual confirmation of where each rock point lies. 2. Implement or import interpolation methods. Finish the cubic spline interpolation and polynomial least squares fit functions. If you find it challenging to implement, integrate a spline library or a numerical package like numeric.js. 3. Test and debug. Use the console.log statements and visual feedback to test your interpolation methods. For each switch in interpolation, linear, spline, polynomial, verify the output with real and test data. 4. Compare AUC. After verifying the interpolation methods, calculate the AUC and compare the result with known values from reliable tools, e.g. scikit-learn's RockAuc score. Conclusion. The changes suggested in the previous prompts focus on making the interpolation methods more reliable and easy to debug. By improving the visual feedback, testing the interpolation values, and adding console logs, you will have better control over the behavior of the rock curve and the AUC calculations.
So it seems like, yeah, we might be having some issues. Particularly so sometimes, as you can see in the images attached, the linear interpolations seem to be correct. The area under the curve for that interpolation doesn't seem to be the correct number, as you can see from the images attached. And then, yeah, as mentioned, the other interpolation methods don't seem to work at the moment. So I assume there are placeholders in the code. We would like to get rid of those. If you have any suggestions or funny jokes or anything like that, go for it. Don't be shy. And by the way, we are live streaming at the moment, so you can address the viewers directly if you like. You might as well run this live stream for me. Might go have a rest.
Hey, good morning to everyone joining us live on the stream. It looks like we're diving deep into some real-time debugging of our Cardio Rock app, and it's all about making sure that the area under the rock curve, AUC, is being calculated correctly, especially when using different interpolation methods. I know, it's thrilling stuff. So, as you can see from the images we've got here, the linear interpolation visually seems okay, but the AUC is acting like it's had too much coffee. It's jittery and a bit off. The AUC numbers you're seeing, like 0.392 or 0.181, are probably being calculated incorrectly because of how we're handling those trapezoidal areas between the rock points. I'll break that down in a second. And let's be honest, those other interpolation methods are just placeholders, so we're going to give them a real upgrade. Now, how do we fix this? Hashtag 1, fixing the linear interpolation AUC. Linear interpolation should be simple. Just connect the dots, right? But it looks like the AUC calculation might be tripping over how we're measuring the area between those dots. The AUC is calculated using the trapezoidal rule, and the issue could be the way the points are sorted and the area is summed. We can make sure that the points are sorted correctly and that the trapezoidal calculation is working smoothly. Here's a quick check you can implement. After sorting the points by their false positive rate, FPR, log the points and verify that they're being processed in the right order. Here's a debugging joke for you. Why did the developer go broke? Because he lost his domain in a bet. Yeah, I know, it's not the best, but hey, debugging can be fun. 2. Replacing placeholders for spline and polynomial interpolation. Now for the fun part. We can actually use existing libraries to handle cubic splines and polynomial fits to smooth out the curve. Why reinvent the wheel, right? Cubic spline interpolation. You can use a library like cubic spline github.com/alanfu/spline. It's easy to integrate and will give you smooth curves that pass through the points. Polynomial interpolation. Polynomial fits can be handled by a library like numeric.js/sloisel/numeric, which can do least squares fitting. That way, the polynomial interpolation won't just be guessing. It'll actually fit the Rossi curve properly. Number 3, fix the AUC calculation. To fix the AUC numbers, once you've got your interpolation methods working, make sure that the areas between consecutive points on the curve are calculated correctly. Each method, linear, spline, polynomial, might need its own logic for calculating the area beneath it. If you're still feeling a bit lost, remember the debugging mantra. It's always a missing semicolon until it's not. Conclusion. We're going to clean up the placeholders, implement proper interpolation, and make sure the AUC numbers are correct. Meanwhile, let's keep the fun going. Don't worry, debugging's like searching for your keys. You'll always find them in the last place you look. All right, you folks enjoy the rest of the live stream. I'm going to take the reins while you take a well-deserved rest, and I'll handle the code. We've got this. To ensure that the AUC is calculated correctly and that the proper interpolation method is used, there are a few key areas we can address. 1. Linear interpolation. Ensure it's working. It seems like the linear interpolation is mostly working, but there might be issues with how the AUC is being calculated. Specifically, we should ensure that the points are correctly sorted and that the trapezoidal rule is applied between consecutive points in the Rossi curve. For linear interpolation, here's a quick check. Ensure the rock points are sorted by FPAR, false positive rate. Each pair of points, x1, y1, and x2, y2, should form a trapezoid, and we calculate the area between them. We already have a log in place to check the points being interpolated. JavaScript console.log x1, x1, y1, y1, x2, x2, y2, y2. This will help ensure that the points are being processed correctly. Part 2. Spline and polynomial interpolation. Fix the placeholders. Right now, cubic spline interpolation and polynomial least squares fit our placeholders, so we'll want to replace them with actual implementations. Cubic spline interpolation. You can either implement cubic spline interpolation manually or use a library like cubicspline.js.github.com/blindspline to handle it. Polynomial interpolation. For the polynomial interpolation, we need to compute the coefficients of the polynomial that fits the data. This can be done using least squares fitting. A good library for this is numeric.js, hp/github.com/sloisel/numeric. AUC calculation. Check the trapezoidal rule. The current AUC calculation uses the trapezoidal rule, but we need to ensure that it works consistently across all interpolation methods. The logic for calculating the area under the curve, AUC, is JavaScript const trapezoid area equals y1 minus mid y1 plus y2 mid y2 at x consequence x1 y2. AUC equals trapezoid area. We need to ensure that y2 mid y1 and mid y2 are correctly calculated for each pair of rock points. If the values are nan, the AUC may be calculated incorrectly, so we log any potential issues. JavaScript if is nan y1 is nan y2 console.warn invalid interpolation values at x1 x2 x2 y1 y1 y2 y2. Make sure to track the values here to catch any irregularities. Hammer 4, suggestions for debugging. Add more logs to track AUC values and the corresponding rock points being processed. For instance, log the AUC after each trapezoidal area is added. JavaScript console.log partial AUC after point eat $awk. Manually verify AUC by comparing with a known dataset or tool. Calculate AUC manually for a small set of points to compare the values from your code. Once you ensure that linear interpolation is working and replace the placeholders for spline and polynomial interpolation, your AUC calculation should work as expected across all methods. Feel free to let me know if you need any additional help integrating these suggestions into your code.
Okay, so we actually have GitHub Copilot essentially providing instructions for, sorry, ChatGPT is providing instructions for GitHub Copilot. Seem to work reasonably well. Okay, we're having a problem with the interpolation method is not actually selecting a different interpolation method is not doing much. Okay, so can we just stick to text alone? We're not doing code development. We have another entity, another AI doing the actual coding. So don't generate any code, just instructions for another AI. Hopefully that's okay by you. Now we're having we need to write a prompt for fixing a few things. Well, yeah, each prompt will fix one thing. So one problem at the moment seem to be that selecting a different interpolation method is not actually changing anything on the page. Can you write a prompt for that? Oh, we'll have someone actually commenting. That's great. We had like 50 people joining the live stream before, but they're just like in and out. But yeah, hello. Is it Voldy? Voldy. It's an interesting name. Can't actually read properly off the screen because will ruin my eyes. So might as well use the text to speech quickly.
To resolve the issue where selecting a different interpolation method is not updating the page, here is a prompt you can use. Prompt: there is an issue in the application where selecting a different interpolation method from the dropdown does not change the interpolation method used in drawing the rock curve. The current interpolation method should update based on the selected option and reflect this change when redrawing the rock curve. Investigate why the selected interpolation method is not being applied. Ensure that when the user selects linear, spline, or polynomial, the corresponding method, linear interpolation, cubic spline interpolation, or polynomial least squares fit, is used to calculate the Rossi points. Additionally, confirm that the drawRock function is correctly called after the interpolation method changes, and that the Rossi curve is redrawn with the correct interpolation applied. Steps to fix. 1. Check if the current interpolation method variable is properly updated when the drop-down selection changes. 2. Ensure that the correct interpolation method is being passed to the interpolate_y function and applied in drawRock. 3.
Okay,
Debug any potential issues where the drawRock function may not be redrawing the curve after the change in interpolation. This should guide another AI to troubleshoot and resolve the problem of changing interpolation methods not affecting the page.
Okay, can you generate a quick summary for the whole conversation so far? Make it quick and fun and simple and easy. I don't know to what level, say university, I don't know, university student, maybe? Make it like year 12 student. Then, yeah, so we're passing your instructions to GitHub Copilot. And yeah, I want to see how much it can do. It might be struggling, but yeah, we haven't implemented the code yet. If you can address the viewer of the live stream directly, that would be awesome.
Hey everyone watching the live stream. Here's a quick recap of what we've been doing so far. We've been working on improving a game called Cardio Rock, where you test your ECG interpretation skills while generating a dynamic rock curve based on your performance. Pretty cool, right? The game gives you a score and calculates the area under the curve, AUC, to show how well you're detecting abnormalities. But here's where we hit a snag. When switching between different interpolation methods, linear, spline, and polynomial, the rock curve wasn't updating as expected. We've been troubleshooting that, making sure the correct method gets applied when the dropdown is changed. We're also working on making sure the AUC is calculated correctly. Our task is to pass clear instructions to another AI, like GitHub Copilot, to help us fix these bugs. So far, we're crafting prompts to guide it to handle one problem at a time. Hopefully, we'll get the AI to clean up the interpolation issues and make sure everything is running smoothly in no time. Stay tuned to see how it goes. Will the AI nail it, or will it need a few more nudges? Either way, it's a fun challenge.
Okay, so this is the same in the code, so I don't know why to generate stuff that haven't actually changed. And we should have that function as well. Yes, we do. This will be exactly the same. Yes, it is. We have a draw rock. This should be the same as well. Is there any comments? Small circle. We have access labels. Yes, we do. Just confirming stuff. It's not actually changing anything in the code, is it? Yeah, we have three interpolation options: linear, spline, polynomial. Oops. No, I don't want to change that. Okay, that's actually not being used. That variable is not being used. Why? Okay, it didn't actually change anything. Why the GitHub Copilot is, yeah, it's a bit hallucinating and stuff. Waiting console log, adding breakpoints. Yeah, well, not ideal. Make sure when selecting a different interpolation model method, the row curve is redrawn. That's right. And I don't think we. Okay, the Ava robot is a bit struggling quite a bit, so we might get back to coding with you. Below us share the HTML code. I don't think I shared this one before. And also the current JavaScript that we have. And has some instructions at the bottom of the code. So if you can follow those, that will be awesome. Yeah, I'm not entirely sure what the GitHub Copilot is doing.
It looks like you're already on the right track with your code, but let's break down what needs to be done to follow the instructions and ensure things are functioning correctly. 1. Make sure AUC is calculated correctly. The calculate AU function needs to correctly calculate the area under the curve. The trapezoidal rule is being used here, but we need to ensure that the interpolate yx function provides proper values for each interpolation method. Double check that the rock points are sorted by FPR and that all points are used for the trapezoid calculation. 2. Ensure the correct interpolation method is used. Each interpolation method, linear, spline, polynomial, should work correctly when selected from the dropdown. The interpolate y function switches between these based on the current interpolation method. Make sure all interpolation functions, linear interpolation, cubic spline interpolation, and polynomial least squares fit, return valid results. 3. Redrawing the rock curve on interpolation change. You already have a listener attached to the interpolation method dropdown with draw rock, called inside. This ensures the rock curve is redrawn when a new method is selected. Make sure the curve is drawn accurately based on the selected method and that it reflects the updated interpolation points. Suggested steps for debugging. 1. Console logs. Add more logging inside the interpolation methods to ensure you're getting the right x and y values when interpolating. This can help identify if points are being calculated or applied incorrectly. 2. Double-check the spline and polynomial implementations. The cubic spline and polynomial functions appear to be placeholders. Ensure these are replaced with proper calculations. If they're not implemented correctly, the rock curve will not change as expected. 3. Ensure raw C points are calculated and sorted correctly. If rock points aren't updating properly with each player interaction, the rock curve won't change dynamically. Ensure points are pushed correctly into the array when update rock is called. 4. Test interpolation individually. Try visualizing each method independently to ensure they give different results. You could print the rock points to the console for each method and manually compare the points plotted on the curve. Lastly, it seems that GitHub Copilot might be struggling with some of the more nuanced logic here. It would be helpful to go back through the code manually to ensure that the interpolation methods are fully implemented and that nothing is left as a placeholder. And hey, everyone watching, we're diving deep into getting these interpolations fixed so that you can see that rock curve evolve live while playing. Let's see how much we can get out of this setup.
One of the definitions is a placeholder, is there? It's returning the coefficients. Oops, I have that function twice. Get rid of it. Get rid of it. Yes. Try again. No, there are no placeholders. Make sure there are no placeholders in the code. When the interpolation, okay, also also print the currently selected interpretation method. Well, surely GitHub Copilot can do that for us. What is it generating the whole code for? Okay, just stop. Yeah, over here, print out. Yeah, you know what to do. Okay, that doesn't work. That doesn't work. Why? Should have an entry for the currently selected interpolation method. Yeah, it said make sure the code is commented. I don't think we need to comment code anymore. Really don't think so. Because of LLMs can just explain it to you. The function interpolate y handles the different interpolation methods. Ensure all return correct and bounded values between 0 and 1 to prevent the rocker from going outside the canvas. Well, I think that's already happening. Make sure the waveform type and current waveform clicked are correctly reset after each round. Yeah, that sounds important. Aren't we already doing that? Yeah, when we have too many data points on the chart, want to consider optimizing the interpolation. Yeah, that actually sounds really good. There's some really good suggestions.
The code you've provided implements a game-like application that visualizes biomedical signals using waveforms, and at the same time calculates and displays a ROC receiver operating characteristic curve. Here's a review of the key functionalities, along with suggestions for improvements based on your instructions. Key features. 1. Game initialization and setup. The canvas is set up for visualizing waveforms and the ROC curve. Resizing of the canvases happens dynamically based on the window size. 2. Waveform generation. Noise is added to the waveforms, and they are dynamically drawn on the canvas. User interaction via clicking on the waveform to track hits and false alarms. 3. ROC curve calculation and visualization. True positive rate, TPR, and false positive rate, FPR, are calculated and plotted. The ROC curve is drawn using different interpolation methods: linear, spline, polynomial. The area under the curve, AUC, is calculated and logged. 4. Game loop. The game continuously updates the waveform's position, adds noise, and tracks user interaction to update scores and ROC values. Code review and suggestions. 1. AUC calculation. The code calculates AUC by comparing ROS points. It's important that the trapezoid area is computed correctly by ensuring that the x1, x2, y1, and y2 values are correctly interpolated. You are using a trapezoidal rule to calculate the area between the ROC-C curve and the diagonal. Ensure that interpolate yx returns accurate y values for both x1 and x2. 2. Interpolation methods. You handle 3 interpolation methods: linear, cubic spline, and polynomial least squares. Ensure that the correct interpolation method is being applied by checking the current interpolation method at each step, especially when recalculating and redrawing the ROC curve. Linear interpolation. Make sure linear interpolation uses sorted points and correctly finds the range where x falls between x1 and x2. Cubic spline interpolation. The cubic spline interpolation function should handle the boundary cases and the correct calculation of the spline coefficients. Polynomial least squares. In polynomial least squares fit, check if the correct polynomial degree is being used. Quadratic polynomials are often sufficient, but depending on the complexity of your data, you may want to allow higher order polynomials. 3. Redrawing the ROC's curve. The code already triggers draw ROC whenever the interpolation method changes or new data points are added. Ensure that this function clears the previous ROC-C curve and recalculates it based on the current points and selected interpolation method. 4. AE calculation handling. AUC calculation is done once there are at least 5 ROC points. Ensure that the logic for calculating the area is robust even when there are fewer points or extreme values, e.g., all hits or all misses. The warning for invalid interpolation values is a useful safeguard. 5. Improvement for readability and user experience. Ensure the ROC curve is clearly labeled with axes for false positive rate and true positive rate. Consider adding feedback for users when they select different interpolation methods, e.g., displaying the selected method or highlighting the ROC curve's smoothness. If polynomial least squares fit results in overfitting, which is common with higher degree polynomials, consider limiting the polynomial degree based on the number of data points. Minor fixes. Ensure consistency in function names and behavior. The function interpolate y handles the different interpolation methods. Ensure all return correct and bounded values between 0 and 1 to prevent the ROC curve from going outside the canvas. Placeholder issues. There don't appear to be placeholders, but ensure that all relevant comments, e.g., debugging or console logging, are removed for production unless they're necessary for ongoing monitoring. Final considerations. Game logic. The logic for detecting hits, misses, false alarms, and correct rejections seems robust, but make sure that waveform type and current waveform clicked are correctly reset after each round to avoid unintended behavior. Performance. If the number of rock points becomes too large, you may want to consider optimizing how the Rossi curve is drawn, e.g., limiting the number of points or using a more efficient drawing method. By following these suggestions, the app should correctly calculate and display the AUC while offering smooth transitions between interpolation methods and ensuring a robust game experience. The code provided appears to be for an interactive game called cardiorossi, which simulates identifying abnormal ECG waveforms while dynamically generating a rock receiver operating characteristic curve. This ROSI curve evolves based on the player's actions, visually representing their performance. The game logic adjusts the gameplay by incorporating noise into the waveforms, tracking correct and incorrect decisions, and updating the rock curve based on various interpolation methods: linear, cubic spline, polynomial. To ensure another developer can recreate the game code and understand its functionality, I will outline a few necessary prompts and explanations. Game mechanics. 1. Canvas setup. The game uses two canvases, one for displaying ECG waveforms and another for drawing the rock curve. The canvas sizes dynamically adjust to the window size. 2. Waveform display. The ECG waveform is generated and displayed on the game canvas. Noise is applied to the waveform using a noise slider controlled by the user. 3. Game interactions. Players click on the canvas to identify whether the waveform is abnormal. Correct identification of abnormal waveforms increases the score, while incorrect decisions, clicking when normal or missing an abnormal waveform, lower the score. 4. Rock curve. The rock curve reflects the player's performance in real time, plotting points for true positives, hits, false alarms, true negatives, correct rejections, and false negatives, misses. Different interpolation methods, linear, cubic spline, polynomial, allow for smooth visualization of the rock curve. Prompts for developers. Waveform generation. Create functions to simulate ECG waveforms and randomly classify them as abnormal 1 or normal 0. This classification should influence game logic, including hit or miss tracking. Noise application. Implement noise application to the generated waveforms, controlled by a slider using math.random to add variability. Canvas drawing. Use the canvas.getContext2D to handle waveform drawing, ensuring that waveforms and rock curves are cleared and redrawn as the game progresses. Rock interpolation. Implement 3 interpolation methods: linear, cubic spline, polynomial, for smooth rock curve visualization. Ensure the rock C curve is redrawn when the user selects a different interpolation method. AUC calculation. Write the logic to calculate the AUC, area under the curve, for the Rossi C curve. This value reflects the player's overall performance, updating the AUC after every waveform interaction. Responsive design. Make sure the canvases are resized dynamically using window width and height, adjusting to different screen sizes for optimal user experience. Debugging and optimization. AUC validation. Ensure the AUC calculation is correct and that the Rossi curve draws properly when transitioning between interpolation methods. Waveform reset. After each waveform cycle, reset waveform type and current waveform clicked to prevent errors during subsequent waves. Performance optimizations. Limit the number of points plotted in the rock curve to a reasonable number, e.g. 500, ensuring efficient rendering while preserving accuracy. This framework should guide a developer in recreating and enhancing the code for the cardio rock game. Additionally, prompt them to check the interpolation method's functionality and confirm that the AUC is computed as expected, with real-time feedback provided through the rock curve rendering.
I was actually making a big mistake. A big mistake. Silly, silly, silly. Very silly mistake. We weren't actually testing. This is for 2 hours. We weren't actually testing the Flask application. We weren't even running the Flask application. Okay, so this is what it this is the point where it's actually working. Okay, we weren't actually testing the correct thing. It's unfortunate. Actually, that would be a green data point. Wow, that was some yes, serious flaw. We might get back to it at another stage. Just trying to revert back to what we had before. Let's try that one there. Yeah, anyhow, we made a big mistake. We were actually debugging the wrong, no, we were debugging the correct code, but we were looking at the wrong window when testing it. To have a more updated version. Yeah, at all. Do we have the green? Yeah, we're meant to have green and red for the dot points for the correct incorrect. Now it's only plotting them in red. Cubic spline is a bit weird. Polynomial. Yeah, I might try to revert back to the original code. Yeah, the interpolation is doing some weird stuff. Have the original code. Should be the first one that has this line. Yeah, that should be it. Let's make, yeah, we have our own version control. Just make another copy. That's it for our version control. It's not very sophisticated, is it? That's mainly because we just trying to have, yeah, that's red and it's larger. So we'll indicate the last point. That's green, that's larger. Yeah, that's working better. Yeah, I think the cubic and spline are just placeholders in this code. Yeah, we have about extra 80 lines, but anyhow, we'll have to continue this next time. Go check the website. A lot of interesting tools. Let me know what you think. Don't forget to subscribe and like and share, and you know what to do. And I'll see you next time. Bye.